All right. First of all, chemistry is a physical science. When you took biology last year, biology is called a life science. Chemistry and physics are considered to be physical sciences. Okay. Whenever we're talking about chemistry itself, the definition of chemistry, it is the study of the composition, the structure, and the properties of matter. It's also the process or the changes that matter undergoes and the energy changes that accompany these processes. Okay. I do fill in the blank notes with you guys, and primarily it's to make me slow down because I tend to go too fast. So I have found that if I write along with you, then I don't go too fast, and then y'all aren't trying to catch up. So that's why I'm doing it that way. So that is the definition of chemistry. You should be aware of that definition. When we're talking about chemistry, there's actually quite a few branches of chemistry that you can study and specialize in. The first one is the study of most carbon-containing compounds, and that is called organic chemistry. If you're talking about yes, you have a question?
I didn't get the last one.
Okay, I'll get it to you at the end, because if I go back, it's not there. Yeah. Organic chemistry is carbon-containing. Inorganic is all the other compounds. If you're talking about the study of the properties and changes of matter and their relationship to the energy changes, that's where we're talking about physical chemistry. And physical chemistry is actually one of the hardest branches of chemistry. We have to take it in college. But it's basically where physics and chemistry meet. Okay? So you can kind of put physics and chemistry meet. Okay? The identification of components and composition would be analytical chemistry. The study of substances and processes in living things. Anybody want to guess what that's called? Biochemistry. Very good. So that's basically where biology and chemistry meet. I just put biology there, sorry. Biochemistry. I was talking about biology and wrote that. So that's where biology and chemistry kind of overlap. Basically, it's chemistry in the body. Any of you want to be doctors when you grow up? You will be studying quite a bit of biochemistry. The use of mathematics and computers to understand the chemical behavior, that is called theoretical chemistry. Okay? Now, within those branches, there's a lot of overlapping with each other. If you are studying organic chemistry, you're going to be doing some analytical in there, okay? Probably some physical in there as well. So a lot of those overlap, but there are people who decide that they really love chemistry and they want to go on and get a master's or a doctorate, and they usually will specialize in a branch. They don't just get it in general chemistry, okay? So the chemical is any substance that has a definite composition. That's what we're going to call chemicals. And just about everything in the world has to do with chemistry. Almost everything. We can break it down to a chemical process. Okay? Okay. Matter. Oops, I skipped one. There we go. So the three basic goals of chemistry. The first one is basic research, and those definitions are already there for you. Basic research is carried out for the sake of knowledge. We're just want to see what happens. We want to try something out and see what happens. We're not really trying to solve a particular thing. We're just kind of seeing what's going on. You know, what happens if we do this, or we discover this unknown compound, and we want to see what are some things that we can do. Many chance discoveries are made through the basic research. Okay. If you have trouble finding it, I already have it all pre-filled out, so at the end you can get whatever blanks you're missing. Yeah, I already have it right here. Okay. The applied research is usually carried out to solve a problem. Okay, one of our big issues right now, of course, is fuel sources. You know, fossil fuels are trying to find alternate forms of energy, and so basic research would be something that they're trying to see if we could, different kind of fuel cells, for instance, hydrogen fuel cells, that sort of thing. So that applied research is, I'm trying to solve a specific problem. And then technological development is when we take that research, things we found out in that research, what can we do to apply it to make our lives better and easier, okay? A good example of that is Teflon. Do you even know what Teflon is? Non-stick pans, right? Teflon is in all kinds of things. Teflon itself was discovered by accident during a basic research. Somebody at DuPont was doing an experiment, and they put all this different things, whatever it takes to make Teflon, into what's called a bomb calorimeter, which is like a sealed, pressurized reaction vessel. And they put this stuff in there, they did the reaction, and they opened it, and nothing came out. And they're like, wait a minute, what's going on? And so they cut the thing open, and all of a sudden there's this stuff coated on the inside. And they're like, that's weird. And so that was discovered during a basic research phase. Then it went through the technological development, like how can we use this? Okay, so technological development usually lags far behind the basic or applied research because it takes a while to see, okay, so we could use this, but is it safe for the, mass public or, different things like that. So the technological development always lags behind. Matter is, and this was our journal question, and no one wanted to answer it, so matter is anything that has mass and takes up space. You could also say has volume. So everything in the world, in the universe, is matter except for one thing. Can you think of something that's not considered matter? I'm talking about physical things that you can see, not ideas. You can't really see ideas. What are, even your thought process in your brain, chemical reaction going on. Okay? Something in this room right now that's not matter because it does not have mass and take up space. Light. Air has mass and takes up space. You just can't see it, but air definitely has mass because the air is full of nitrogen, oxygen, hydrogen, but it's light. Light does not have mass or take up space. Okay? Mass is the measure of matter, so how much matter is present. Volume, of course, is the amount of three-dimensional space that an object occupies. Just because we can't see it taking up space doesn't mean it does. So, for instance, air, we can't see it, but it's definitely taking up space. This room is filled with air right now. Okay? The building blocks of matter are called what? Atoms, yes. Okay? And then within atoms, they make up our elements. Okay? So everything, every chemical that you can ever think of is going to have atoms or elements which are made up of atoms. Okay? Of course, an atom is the smallest unit. I'm too serious deciding to act up. So an atom is the smallest unit of an element that maintains its chemical identity. Okay? Notice it's not the smallest type of matter. You can have protons, neutrons, and electrons. Okay? But an atom is the smallest one that would retain its chemical identity. Okay? An element is a pure substance that can't be broken down into any simpler substance. Okay? So an element is a pure substance. So that brings us, before we talk about classification of matter, because we can't really classify matter unless we can understand physical and chemical changes. So today we're going to talk about physical and chemical changes. The packet that you picked up today, if you noticed when you came in, it's not due until Monday. So because we're going to go through physical and chemical changes, but not classification until tomorrow. So it's due on Monday. Okay? All right, so all matter has characteristic properties, and these properties can be used to identify that matter. The first type we're going to talk about, which is a type of physical property, And that is physical versus intensive properties, okay? I mean, extensive versus intensive, okay? The first one is an extensive property. And that is something that depends on the amount of matter present, not its identity, okay? So a property could be its volume or its mass or its length. That is an extensive property. It kind of, basically you can kind of, it depends on the extent of matter that you have. The second type is intensive. And intensive properties do depend on the identity, okay? So an example of that is boiling point. The boiling point of water is, anybody know?
200 degrees.
It's 100 degrees Celsius. Okay, we don't use Fahrenheit in here. So the boiling point of water is 100 degrees Celsius. It doesn't matter if I have a cup full of water, a big, huge beaker full of water, or a huge bathtub full of water. No matter what, the boiling point of water is always 100 degrees Celsius. Doesn't matter how much I have, okay? Now, obviously the larger amounts would take longer to boil, but the boiling point would still be 100 degrees Celsius, okay? Density is another example, okay? If I have a metal, and when we get to the measurement unit, we're going to do a density lab, but let's say I have copper, and the density of copper is, I can't remember off the top of my head, but let's say it's 8.9, okay? If the density of copper is 8.9, it doesn't matter if I have a pellet of copper, a big old chunk of copper, or a huge ball of copper. It's always going to have the same density because that is part of its intensive property, okay? So the way that I help kids remember it is identity and intensive both start with I, so they go together. Intensive depends on the identity. And can be used to identify, okay? So if I had this unknown metal and I figured out its density, I could use that along with some other things to help identify that that unknown metal was, say, aluminum, okay? But if I have 400 grams of something, that's not going to help me identify anything. I could have 400 grams of feathers, I could have 400 grams of marbles, or 400 grams of chocolate. Prefer the chocolate, but the 400 grams itself would not help me identify the identity of the substance. But an intensive property can, okay? And then we have physical versus chemical properties, okay? A physical property is a characteristic that can be observed without changing the identity. So physical means I can observe it without changing it. So in other words, if I boil water, is it still water? Yes. So that would be a physical property. The boiling point of water is 100 degrees Celsius, okay? It's still water after I boil it. Now it's just steam, but it's still H2O. So that would be a physical property, okay? If I look at the color of something and I say copper is that reddish color, okay? Can I observe that without changing the copper? So that would be a physical property, okay? A chemical property is something that describes the ability of a substance to undergo a change, okay? So gasoline has the ability to burn. That is a chemical property because when I burn something, it's not the same when I finish, okay? Iron has the ability to rust, okay? So that, and when iron rusts, it's no longer iron, it actually becomes iron oxide because it's got, that's what the red stuff is its oxygen has combined with the iron to make a new substance, which does not have the same properties. So a chemical property is the ability to undergo a chemical change. Okay? Keep having to change colors because the slides are different colors. Okay? Now, in terms of changes, okay, physical properties are the observing of it. The physical changes is they're actually happening. So physical changes, okay, changes the form of the substance without changing the identity. Okay, so the properties are remaining the same. So if I take a piece of paper and I tear it, is it still paper? Yes, I didn't change the structure of the paper. I just have two pieces of paper now. Okay, if I had, say, take some cinnamon sticks and I stick them in a grinder and I grind them up really, really fine, do I still have cinnamon? Yes. I just have little small pieces of cinnamon, but it's still cinnamon, okay? Phase changes, this is one that gets kids every year. Changes of state are always a physical change. And we just talked about water. If I boil it, it becomes steam, but it's still H2O, right? What happens if I freeze water? It becomes ice. What's the formula of ice? Yeah, it's H2O cubed. Okay. No, it's still H2O. It's just a little joke. So the structure is all the same, okay? Doesn't change. And that is probably one of the biggest mistakes about physical changes is I say, I melted something, and they'll say, oh, that's a chemical change. No, it's a physical change, okay? Because I'm melting. If I melt chocolate, it's still chocolate, okay? Whether it's in the liquid form or the solid form, okay? Chemical changes, excuse me, chemical changes or a chemical reaction is a change in substance that involves it changing into a different substance with a new identity, okay? And the properties of the new substance will be different. So I'm I'm chemically changing it into something different, okay? For example, burning charcoal, okay? If I burn charcoal, let's say, you've all seen the little charcoal briquettes if you're going to barbecue. When you're done burning them, what does it look like? White ashes, and it's very, very powdery, right? And then, of course, you've given off some water vapor and some CO2 vapor. So that is a chemical change, okay? When iron actually does rust, it is a chemical change because it's no longer the same, okay? So those are those differences. I would go back if I were you and kind of circle this because I can't tell you how many times people make that mistake. So kind of make note of that. Physical changes are always physical. Phase changes are always physical. They both start with pH, right? Phase, physical. Phase, physical. Okay. So let's talk about how we know if a chemical reaction happened. Okay. So we're going to be doing lots of chemical reactions as the year goes on, but for right now, let's talk about how we would write it as an equation. Okay. And this should be an arrow here, not an equal sign. I don't know why it's an equal sign. We don't ever write equal, we write an arrow. So change that to an arrow. Is it an arrow on your notes? Yeah, I don't know how that happened. Okay. So the reactants are always what comes before the arrow because they have to react together. And then the products are always after the arrow. Usually we read that arrow as yields. So reactants yields products. Okay. These are some of the indications of a chemical reaction. Okay. Heat or light is produced. Okay. Also, heat could be, I would say heat, let's go and say heat changes or temperature changes. Because some reactions actually will feel colder. Okay. Do you remember what those are called? If the reaction puts off heat, it's called what? Exothermic. And if it takes in heat, endothermic. Okay. So those are the two. So y'all at least remember that. That's good. I like endothermic reactions personally better because I think they're cooler. So if a gas is produced, okay, I love corny jokes. If y'all have corny jokes, bring them to me. I love them. Okay. So if a gas is produced, how would I tell if a gas is being produced? Let's say I mix two liquids together and a gas is produced. How would I see that? Bubbles, yes. You're one of the first ones to ever get it right off the bat. Usually they're like, you can see it, you can smell it, but what if it's odorless? It's bubbles. You would see it bubbling, and because that's the gas escaping that you just produced. Unless it's a Coke, that's different because that's already been put in there, and that's just coming out of solution, okay? If a precipitate is formed, okay, and what a precipitate is I mix two liquids together that are clear, and I can see through them, may not be colorless, but they're clear, and I mix two liquids together, and all of a sudden I have a goopy or a gunky or a solid falling out of solution to the bottom. Okay, that means I had a chemical reaction. I made a precipitate, and then color change and odor. Okay, we need to be a little bit careful with color change. Okay, a little bit careful with color change, and that's because sometimes color change is not necessarily always a chemical change. Sometimes it's a physical change, but you've got to think about what you're doing. For instance, if I have a glass of water and I take one of those little packets that I can flavor my water with, and I put it in there, what happens to my water? Turns whatever color. That is not a chemical change. That's just I dissolved something that had color. Okay? So you got to be, don't always think that, oh, I mixed it and it changed colors, it must be a chemical change. No, I happened to dissolve something that was like pink and made that pink. Okay? Dissolving is going to always be a physical change. Because if I dissolve something in water, how can I get it back? If I dissolve Kool-Aid in water, could I get my Kool-Aid back? I could boil it, boil off the water. It'd be a nasty, sticky residue, but I could separate them back out by taking out the water. Okay. All right. So did this thing just freeze up on me? It's not going to the next slide. Come on. Okay, I think it just froze on me. There we go. Okay, so let's practice some of these. Water turning into steam, what kind of change would that be? Or what? Physical. We'll put a P there for physical. Density. Density is a physical property, but it's an intensive physical property. So we're going to say intensive physical. Okay? Because I can view the density, I can take a metal and go figure out what the density is, and I don't change it. So that part's physical, but it's an intensive property because it depends on what it is. How about mass? So that would be extensive physical. Because I can obviously observe mass without changing it, but it's extensive. How about digestion? Digestion itself, I'm not talking about the whole process of eating. I'm talking about when you swallow food and you digest it, would that be physical or chemical? Chemical. It does not come out the way it went in. Okay? Freezing point. It is physical, but we're also going to say that it's intensive. Okay? Because it depends on what it is. Freezing point of water is different than the freezing point of ice cream. Okay? Ability to rest. Chemical. Okay? So if something's a physical change, we need to also further classifying it to be intensive or extensive, so we can think about in those terms. Okay? So density, we said, would both be, we already said that, we already answered that. It's intensive and physical. So we answered that question. Okay? This is from last year. Y'all don't have to do this. And then we'll talk about the states of matter, and then that's where we're stopping today, so you can maybe work through some of those examples. Okay? So there's the states of matter, of course, that we know of are solids, liquids, and gases, and then we'll also talk a little bit about plasma. Okay? Somewhere in your notes, if you have room, you should be drawing these particles and the way they look for each one. Okay? Especially for those of you that may go on to take AP Chem, they're big on the part, it's called the particulate view. Okay? And of course, from junior high science, we know that, solids have a definite shape and volume, okay? But in terms of kinetic energy, they have a very low kinetic energy, okay? The particles are able to vibrate in place, but they can't move around, okay? And basically the kinetic energy of matter states that all particles are always in motion, okay? All particles are always in motion. So even solids are vibrating in place. They're moving a tiny, tiny bit. So right now you're sitting on vibrating particles, okay? An example of where you can feel that is, have you ever been sitting at the light and someone drives up and they've got their bass like really, really high, right? And then you feel it going boom, boom, and you kind of feel your car vibrating. If those particles of a solid weren't able to vibrate in place, you wouldn't actually feel that, okay? They have a definite shape and volume, okay? And of course, if you look at their particles, they're arranged in a very orderly and structured fashion. They're very close together, and they're very orderly fashion. So I would draw something to that effect next to your solids, so you can kind of know what they look like. give you a second for that. Okay. Liquids, what do we know about liquids?
The molecules slide past each other.
Yes, very good. They also have a low kinetic energy. They have more kinetic energy than solids, but they can move, but are very still close together, and they can be thought of as sliding past one another. They glide over each other. Okay. What about their shape and volume? So they have an indefinite shape, or we'll call it a variable shape, because they take the shape of their container, but they have a definite volume. There is a fixed amount when you have liquids. Can you compress liquids? No, we cannot compress liquids. Okay. So if you look at those particles, they're still very, very close together, but they're all haphazardly arranged because they're constantly, you move the container, they're constantly moving and flowing past each other. Okay? And then, y'all ready for gases? Okay. And then, of course, gases have a very high kinetic energy. Because their particles are always moving very, very quickly. Okay, so they have a very high kinetic energy. The particles can, what did I say? Oh, separate. They're almost all, and this is one of my pet peeves. Please spell separate correctly. I can't tell you how many people spell it wrong. It's P-A-R, not E-R. And move freely throughout their container. They can separate and move freely. Okay, and of course they have a variable shape and volume. They will fill the container that they're in. Okay, so if I was to release a gas in here, the particles would fill this room, and some of them would actually go under the door and crevices where there's little holes they can get through. Okay, so they're far apart and they can move freely about. Okay, that's why when someone sprays perfume, you can smell it across the room because the particles of the perfume spread throughout the room. Okay? We'll talk about just spraying perfumes, that smell spreading across the room. We'll talk about the other kinds. And then the last state is plasma. And plasma has a very high kinetic energy. In fact, so much so that the particles collide. Oops, I forgot to, sorry. If I don't hit the button to say I'm writing, the particles collide with enough energy to break into charged particles. Okay? They are gas-like in their behavior, meaning that they have variable shape and volume. Okay? And of course, examples include things like stars, the fluorescent lights in the room are plasma, and then cathode ray tubes. Used to be plasma TVs were the big rage. They don't really have plasma TVs much anymore. But that was, it doesn't feel hot because it's moving so fast, but it actually, the sun is plasma as well. Okay? And then you don't have to do that. And then that's where there's just an example of some plasma just to look at. Neon signs are plasma. Lightning is plasma.